Hey, welcome back, everybody. So we want to talk about the first type of line integral that could describe the mass of a wire that has variable density f. And so we've got two forms here. So we've got one for a line integral in R2 and one for a line integral that's in R3. And so here we've got the line integral over the curve C of f of xy ds, and ds is exactly this quantity that should remind you of the arc length element from Calc 2. Or we could have this form, which is similar in R3. And so for this, let's go ahead and look at a version like this. So let's suppose we have the following situation. So let's say we want to evaluate the line integral over C of quantity 2 plus x squared y ds, and C is exactly the top half of the unit circle. So let's say that. So where C is the top half of x squared plus y squared equals 1. Okay, so again here, if we want to think about this as the mass of a wire, this is my density function. And then my wire is represented by the curve C, which is the top half of the unit circle. So our first goal should be to parameterize our curve C. So let's take a look at this situation. We have the following. So we've got the top half of the unit circle. Okay, so this is the curve C. And so we're going to go with the traditional way to parameterize this. And we're going to say x is equal to, so if we want to be on the circle, not inside the region, but on the circle, then we want x is equal to the radius times the cosine of t. So that's 1 times the cosine of t. So if you're wondering where the cosine of t comes from, just pick any point that's on the circle and form a right triangle. Call your angle t, so your parameter is t. And then this distance, of course, is x, and this distance here is y. And since that's the unit circle, the radius, of course, is 1. And then if you take the cosine, that tells you that the cosine of your angle is x. And similarly, if you take the sine of the angle, sine of t, that tells you that the sine of t is y. You can check that this is valid just by plugging x in for x, y in for y, and you get a true statement, right? You get that classic Pythagorean identity that cosine squared of t plus y squared, or sine squared of t is 1. Okay, but since we only want the top half, we want our parameter t to go from 0 to pi. Okay, so that seems pretty nice. So here's the problem. We're able to describe our curve parametrically. And so what else do we need? Well, if you think about it, we also need a ds. So we know that ds is equal to the square root of dx dt quantity squared plus dy dt quantity squared. And that's dt, right? So we want to figure out exactly dx dt, dy dt. Well, that's not too bad, right? We know what x is, we know what y is. So we just need to take the derivatives and square them. So dx dt should be minus sine of t. We want that quantity to be squared. And dy dt, that should be exactly cosine of t. We want that quantity squared. Okay, well, that's not too bad. So when I square that, I get the following. So that's going to give me sine squared of t plus cosine squared of t dt. But that's exactly the square root of 1 because, again, that's that classic Pythagorean identity, dt. And so ds should be 1 dt. Okay, so that's going to be handy. So let's see what we're left with here. So let's go ahead and compute our line integral. So we've got the integral over c of 2 plus x squared y ds Okay, well, our parameter t goes from 0 to pi, so the bounds correspond to our parameter. So this goes from 0 to pi. And then let's see here. So we need 2 plus. Now we need to take x, which is cosine of t, right, and square that. So that's going to be cosine squared of t. And then we need to multiply that by y, but y is exactly sine of t. And ds, we calculated ds to be exactly dt right here. So that's dt. So this is pretty nice. It sort of looks like a traditional, maybe Calc 2 or Calc 1 style problem at this point. And let's see here. So maybe because these terms, so here and here, they require different techniques, maybe we could split them up into two separate integrals. That might be a good idea. All right, so since the integral is additive, we can write this as the integral from 0 to pi of 2 dt plus the integral from 0 to pi of cosine squared of t sine of t dt. Okay, so this is not bad. We know that theorem from Calc 1, that the integral from a to b of a constant dt is that constant times b minus a. So that's going to give me 2 pi. And then this integral looks like a classic substitution. So for our substitution here, we're going to say u is equal to the cosine of t, right, the inside function here. Now the derivative of cosine, of course, is minus sine, but I'm going to bring or multiply both sides by -1, bring that negative to the other side. So I've got this. All right, so that's good. Don't forget to, of course, change the bounds. So what do I have here? So let's think this through, right? So if I plug in 0, cosine of 0 is 1. If I plug in pi here, cosine of pi is -1, so that'll be the integral from 1 to -1. But that's negative, and we know if we switch the order, that will get rid of the negative. So instead of going from 1 to -1, since the negative we can take care of by switching the bounds. So this will be the integral from -1 to 1. So here we've got u squared du. Since this is an even function, you could use symmetry, right? You could write this as 2 times the integral from 0 to 1 of u squared du. That'd be fine. I'm going to solve it as is. All right, so here we get u cubed over 3 from u equals -1 to u equals 1. So that gives me 2 pi plus, looks like 1/3 minus -1/3, but that's exactly 2/3. So the value of our line integral is 2 pi plus 2/3. And remember, this kind of integral could represent the mass of a wire that has variable density, right? So this would be the density function. At each point on the wire, this would tell you the density. This will give you the total mass of such a wire.